Hey everybody. Sarah, Cameron, Alex, Justin all said hello, but there's only one person in the chat in the thing now, which is kind of weird to me. Hello, hello, hello. Good evening, everybody. Is anyone gonna make a study guide for the AP? Oh no, Cameron. Great question. Hi, Eric. Hey, Atun. Good evening. Hey, Maya. Hello. Hello, Jacqueline. So, on a scale of 1 to 10, how good do we feel about the problems? Give me like 10, like 10 comma 10, or like 8 comma 6, just depending on like that divided into the first problem and the second problem. Like, how do we feel about the two problems that were handed out? 7 to 8 on both. 8 and 8. This is good. This is good. This is pretty much, I would say, probably the hardest unit that's covered on the AP exam, right? I think it's probably the most specific in that, like the formulas you need to know and the concepts are like really focused, but it's more difficult. Whereas I think conservation of energy is kind of easy, but it has like a very broad range of applications, right? So they're kind of opposite. 5, 5, 8, 5, 5, 5. All right, cool. All right. So let's go ahead and look at part A for number 1. Let's do our regular thing here. Okay, so this is a statics problem, which means you're allowed to choose your pivot, right? So all I have to do is see if this is my center of mass, there's a gravitational force acting there, right? And if I choose this to be my pivot, okay, and I choose my thing to be at point C, okay, well, if the torques are equal, then FC is less than FG, right? It's pretty clear, right? If I choose my thing to be at point B, then FB is equal to FG. And if I do my point, if this torque is equal to this torque, then FA is greater than FG. And then the ranking kind of follows. All right. Some of you might take issue with my assumption of putting point B at the exact same location as FG. Fine. It's not necessarily true. Here's the alternate way to look at it, okay? Sarah, if you email me the PDF, I can distribute it to the whole class if you want, okay? Right after this optional review session, okay? So the rule basically is the torque due to whatever string equals the torque due to gravity, right, which is, I'm going to call this length L, where this is like L, mg, and this is equal to the torque supplied by the string, whether it's here, here, or here. And that has to be R times the tension, right? So you have to notice that no matter where you put the string, the torque that is the string, supplied by the string, is going to equal the same thing no matter what. So which string has the higher tension? It's the one with the lower radius. All right. Cool. Sarah, don't apologize. Quit apologizing. Okay. So let's move on to question B, if you have no more other questions. All right, so then they hang it, but it snaps, so it falls from this position to this position to this position to then this position. It has the greatest alpha here, the next greatest is here, and the smallest alpha is there. Why? Because I alpha equals the torque, and torque is R cross F. And there's F, right? F is always this F, and then, but it's the F that's perpendicular, right? So I'm talking about that component of F. And the more it has fallen, the smaller that component is, right? Cool. If there are no questions with that, I would love to move on because I have not made dinner yet, okay? Show that alpha can be are you serious? Okay, so all right, so the rotational inertia, okay, so torque equals I alpha, and that's 1/3 L squared alpha, and this is L over 2 F sine theta, Fg sine theta. Okay, where I need to see how they calculate theta. All right, so the problem with this, the way this problem is formulated, is that they don't tell you what theta is. Okay, I am defining theta as the angle between F and the rod. So this is theta. Okay, not that. Okay. All right. Why am I using L over 2? Because the force acts there, so the R in like R cross F is there, right? That's the R, so it's L over 2. And then if you do it this, it's L, and this is what? M times G, right? So alpha is, the M's cancel out, amazing. One of the L's cancels out, so this is sine theta over 2 times 3 times L, which is sine theta over 6L. What? My answer is not that. Oh, because this 3 goes on top, sorry. There. And that's the answer. Amazing. Okay. Number 3, C, students want to describe the angular velocity of the sign, and they propose that the following equation, omega of t equals that times t. Regardless of whether or not this equation is correct, hint, it is not. Does the equation make physical sense? No. Okay, so there's a lot of reasons. One, theta is always changing, so you can't. All right, so you guys should be looking at the sheet and not me, right? So you shouldn't be tuned into the actual stream, right? You should only be using this for audio. All right, but for those of you who are like watching both, I'll write this down. Can omega t equal basically a times t? That's what they're really saying. Yikes, 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 okay. Omega as a function of t is equal to at, which is equal to 3 sine theta over 2l t. Does this make sense? No, because theta is not a constant number, so it's going to change. But other than that, what this says is as t goes up, omega gets bigger and bigger and bigger and bigger and bigger. And that really makes no sense, right? Because why can't omega just get bigger and bigger and start spinning faster and faster and faster and faster? Because the sign will just go like this, right? So there's actually a maximum omega that it oscillates. So the omega function has to oscillate. It can't increase linear with t, okay? Students attach a rotary sensor to the sign, record omega and theta, and create a graph of the magnitude of omega versus theta shown. This does make sense, right? Where do I have 0 omega? When the angle's at 90, which is here, right? Where do I have the maximum omega? When the thing is at 0 degrees, which is here. So this point is 90 degrees now, and then this point is 0 degrees, right? That's the thing you gotta know, right? And of course, like by the time it's fallen all the way there, whoosh, it's gonna be the fastest, right? 4 students independently derive equations and propose them to describe the motion of the sign. Which equation best matches the data collected? Yikes, okay. So the easiest thing to do here is whoa. All right, so at theta equals 90, I need to be 0 degrees, right? So that eliminates the things with sine. So it's either going to be the first one or the second one, right? So omega of theta has to equal either root 3g cosine theta over L, or 3L cosine theta over G. Okay, which one is it going to be? Well, think about it now. Like, if I increase G, if I increase my gravitational constant, my rod should be faster at the bottom. Because increasing G, you can think of it this way. If I have my center of mass here and my center of mass here, my gravitational energy changed by mg L over 2, and all of that goes into 1/2 I omega squared. All right? So the more gravitational potential energy I lose, the faster my omega will be, and I increase that with g, right? So I have a bigger omega with a bigger g, and boom, it's going to be this one then, because g is in the denominator and not the numerator. The other way to think about it is just torque, right? Like, of course, the rod with a larger torque is going to have a larger omega. So if I have, well, how do I maximize torque? Well, if I increase g, my torque will increase, won't it? Okay. Phew. Any other questions for number 1 before we move on? I'd be happy to answer anything. Okay. Any general question, even if it's not specifically related to the problem, please ask. Now is the time to, if you increase L though, won't torque increase too? Yeah, but don't you increase I? Yeah, you increase the torque, but you also increase the I. And not only that, I has an L squared term. So if you double length, for example, you double torque, but you quadruple the moment of inertia. So you half the alpha, right? You make sense. All right. If there are no other questions, I'd love to go on to number 2. This question is a short free response. A ramp of height h naught. Okay, cool. Okay. Why is it cosine and not sine? Dimon, if you look at the graph, it hits 0 at 90 degrees. That's what cosine does. Sine hits 1 at 0 degrees. So it'd be impossible to, right? This is not that, the reason, the way I eliminated both the signs was strictly a math problem. You look at the shape of that graph, there's no way it can have sine in it, because if I put sine in there, it can't get to be 0 at 90 degrees, and this graph clearly shows that it's 0 at 90 degrees, right? Okay, moving on to number 2. Blah, 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 blah. Okay, so you're very welcome, Dimon. Dimon, did you know you're in my top 34 in the class? And not only that, out of all the people tuned in on the stream, you're in the top 11. Okay. Okay. So here I am. Gravity, normal force, friction here. If there were no friction, it wouldn't even roll. It would just slip and slide, right? So the fact that I want this thing to roll means I need some friction pointing there, right? That friction is actually what produces the torque, right? Because if you look at this is my pivot, and I exert a friction force this way, that's what causes this thing to spin. Gravity cannot cause a torque because it acts on the center of mass. So the torque due to gravity here is 0 because R is 0 here, right? Same thing with the normal force doesn't work because the normal force is right here. And even while there is an R, there's no component of the normal force that's perpendicular to that R, right? So both the normal force, right, that acts right here, and the gravitational force that acts right here, exerts 0 torque. Okay, so the only thing that exerts torque is friction, and that's why the thing spins. So it's 3 forces, right? It's just like a box. After it's released from rest, the hoop rolls on the ramp, launches horizontally off the table, and lands a horizontal distance d from the edge of the table. The situation is repeated, but the hoop is replaced with a solid disk of rotational inertia, ID. Okay. Okay, cool. In a clear, coherent paragraph-length response that may also contain figures and equations, predict which object the hoop. Okay. Okay. Whew. This is one of those things where I feel every student should get if they think about it. Some of you may not be able to do this in the allotted time given on the exam. That's not what I care about, okay? What I care about is that you guys have the tools to be able to think about this and solve it on your own time, okay? That's what physics is all about. I hate timed physics, okay? So if you guys find yourself in that bubble where You know, like you can solve these, but just not under the time constraint. It's okay. I won't think any less of you. I just won't write your recommendation. Okay. So that's not what life is about, right? Life's not about how quickly you can do things and stuff. So I want everyone to think about this. Intuitively, I know which one, right? No, I'm not even going to start that way. I'm not even going to start that way because I know some students kind of panic if they don't know the right answer to begin with and they don't know how to formulate the answer. So I'm going to do a think aloud from the perspective of a student who doesn't know whether it's the hoop or the disc. It's the disc. And this is an authentic experience, everyone. This is the first time I'm trying to solve the problem. I literally just found these this morning, skimmed through them, and decided, oh, I'm going to give it to them. And this is the first time I'm trying to solve it. So you're literally going through my own process of how to solve this. Okay? So I know that both objects, when released from the ramp, have just a purely horizontal velocity, right? So the velocity is just equal to Vx at that point, which means that like the feather, like all projectile problems, like I know that because since they both have an initial y velocity of 0, an identical y acceleration of negative 9.8 meters per second squared, and an identical delta y of negative h naught. You have to write this in a full sentence, by the way, right? So the way I would say it is, because they have an initial y velocity of 0, the same downward y acceleration, and the same downward y displacement, I can say they're in the air for the same amount of time, right? So the time they are in the air is the same, right? If I model my horizontal displacement from there to there, it's a simple projectile problem, and it's just your x velocity times the time. And since they both are in the air for the same amount of time, the projectile, the object that travels the furthest is essentially the one that has the greatest x velocity. At that point in time, I already mentioned that since there's no y velocity, the object with the x velocity is the actual velocity or the speed, right? So now this has become a problem of just finding which object is faster at that point at the bottom of the ramp. And to do so, we got to use conservation of energy, right? So we have gone from projectile motion to conservation of energy, okay? So using conservation of energy, I know that the potential energy I start off with, ignoring any form of heat, is going to be translated into two different forms of kinetic energy: the translational kinetic energy and the rotational. Okay? Do these things have the same? Yeah, so they have the same mass and the radius. That's great. So both objects start off with the same gravitational energy, right? So they both start off with this much. All right, great. And that gets turned into kt plus kr, right? So this is 1/2 m naught v squared. This v is what I'm interested in, okay? Plus 1/2 I omega squared. And omega squared, because it's rolling without slipping, I can write r omega is v, and then omega is v over r. Okay, so this becomes v over r, v squared over r squared. And clearly here, when I solve for v, right? Well, let me just solve for v squared. V squared is m naught g h naught all over 1/2 m naught plus 1/2 I over r squared. And it's clear the object with the larger v is the one with the smaller radius. Okay, or the larger radius. The I mean the radiuses are the same, right? Whoops. All right. So it's clear that the object with the larger v is the one with the smaller denominator, and I get a smaller denominator with getting a smaller I. Okay. So I think that this part was easy enough to write. This above part was easy enough to write in a paragraph, right? Let's reiterate that, right? They both have an initial y velocity of 0, same y acceleration, same y downward displacement, which implies that the time in there is the same. And if I model my my horizontal displacement as just horizontal velocity times the time, because the times are the same, the object with the greater horizontal displacement is actually just the object with the greater horizontal velocity. At that point of release that I'm talking about, the horizontal velocity is just the resultant velocity because there's 0 y velocity. So the object with the greater velocity here, which is just the speed, is the thing, is going to travel faster. So I'm now looking at a point where I need to find out which one has a greater speed. Then I use conservation of energy, where u equals, for both objects, u would equal kt plus kr. They both have the same amount of u because they have an identical mass. So it just depends on the proportion between how kt and kr are split. You can actually explain this math, but I would go to take a shortcut and say, since rotational kinetic energy equals 1/2 I omega squared, the hoop has a larger, always a larger moment of inertia, which means it has a larger rotational kinetic energy than the disk, and so its translational energy is smaller, and it's going to be slower. All right. What's the very last step, sir? This, I think, is a really bad problem because the math here that I've kind of laid out is very difficult to explain in words. The division thingy. All right, so if you understand the math, that's enough. It's difficult to describe in words, and I'll give you that. Okay, so I basically have for both cases mgh equals kt plus kr, and I'll substitute the formulas for those. So it's just 1/2 mv squared plus 1/2 I omega squared. But omega is v over r, so this is 1/2 v squared over r squared. Then I factor here, okay? And I say this is equal to 1/2 m naught plus 1/2 I over r squared over, times v squared. Right, I basically take the v squared out and leave this stuff in. And then I divide both sides by this, so I get v squared equals mgh all over 1/2 m naught plus 1/2 I over r naught squared. Without looking at that math, though, Sarah, what I can also say is they both have the same ug. So whichever object has the smaller kr has the bigger kt. And kt is the thing that determines how fast I am translationally, right? And because the disk has a smaller I, it has a smaller kr. Boom, it has a larger kt, right? So that's the easy conceptual way to do it. But if you really want to show it mathematically, which I think is important too, you can do it this way. I know this work is really messy. Feel free right now to take a screenshot and then just work over it a little later, okay? I know it's really messy. I'm really sorry about that. I'm trying to save paper. You know how it goes. Each of these is $20. The conceptual way makes sense, but how would you know to take that step factoring? How would you know? Well, you want to solve for v, right? Your your goal is to solve for v. Why is your goal solving for v? Because you want to know which one has the greater v. So you want to express v in the other variables. So then the only way to solve for v here is to factor it out and then divide it out, right? Now, if you're unlucky enough to get like a v and a v squared there, you can't factor. You got to solve using quadratics. But because they both had a v squared term, I can factor. Itamar, good evening. I forgot to send the prompt set for Play-Doh. I will do that around 10 p.m. tonight. I have to make dinner after this, and then, yeah, but I'll do that. When are you done? Can I ask a question about impulse and rotation and the rotational equivalent? I feel like if no one else has a question, I'm done. We can say we're done, and you can ask that question. Good morning. Well, what question would you like to ask about linear impulse and angular impulse, Itamar? Who's Snickety Snack? I'm not going to answer the question unless you identify yourself. Do you remember that question on the test about the door and the clay ball? Yes, I do. And for Snickety Snack, yes, I said they both have the same downward acceleration, right? What formula justifies that? I don't know. Delta y equals VIT times 1 plus 1/2 a delta t squared. So if delta y, a, and vi are the same, of course, delta t is going to be the same. Oh, okay. So it's getting hot. But my window is like banged on open. It's so weird. Hold up. Oh, that's why it's hot. I'm making chicken stock, everyone. That pot over there here has been on a low flame for 6 hours. I was wondering why it was so hot. Okay, makes a lot more sense. I'm actually going to turn that off now because I'm pretty sure it has a good flavor. Let me just get a spoon for a second. Oh, that's good. What do you mean, calm down? Excuse me? Excuse me? Telling me to calm down. Who do you think you are, huh? I would agree with Ayanami, but it was weird and difficult. Okay, so for those of you guys who want to know about that problem, stay tuned. For those of you who were just here for the review of the other problems, you can leave. So the problem was, from a bird's eye view, this door's at rest, and I throw a ball. One's clay and one's bouncy, right? So one of the balls sticks, and they go like this, and the other ball bounces backwards, and then the door goes this way. And I'm saying, which one does it fit? So the first way is a conservation of momentum problem, right? So this ball has an initial linear momentum, right? This P equals mv, right? Its angular momentum is r cross P, which is this r, right? Okay, where r is the length of the door. Cool. Um, at the point of impact, you could say the bouncy ball has greater impulse. Why? It switches direction. Okay. So that means it also has, which means its change in P is greater. Which means its change in L is greater. Right? Because L is just R cross P. Right? So if my P changes a lot, then my L changes a lot. Since the total change is 0, right? That means the change in angular momentum for the door is the same as the change in angular momentum of the ball. So wherever the ball has a greater change of angular momentum, the door has a greater change. That's the first explanation. The second explanation is to say, assuming both types of collisions take the same amount of time, change in momentum equals force times time, right? So if the sticky collision and the bouncy collision took the same amount of time, then the bouncy collision, the door exerted a greater force on the ball during the bouncy collision, right? Because the bouncy collision had a greater impulse, same time, so it had greater force. But by Newton's third law, if the door exerted a bigger force on the ball, then the ball exerts a greater force on the door in the bouncy case as well. If the ball exerts a greater force on the door, then it exerts a greater torque on the door, and then it would cause it to have a greater alpha, right? And since change in omega is alpha times time, and we already went over the time is the same, then the door with the greater alpha is going to have a greater change in angular momentum. Yeah, that's the second explanation. And it really takes into account that the time of the collision is the same in both cases. Yeah. And if you didn't really utilize that, then the problem would be impossible and very weird and very difficult. Okay, so I understand. Okay. Yes. All right. So that's all we need to know. That's all we need to know, right? I'm foregoing review tomorrow. I myself need to take a personal breather. Source of this problem was an old test. But you know what? We'll do this tomorrow too. We'll do momentum tomorrow. Okay. And yeah. All right. I'll see you guys. Have a great night. See you tomorrow morning.